The autocorrelation function is vastly useful in signal processing, so we're going to spend a little bit more time talking about the autocorrelation function. Right now we're going to assume that we have Whiteson stationary process, x of n, and I've put the definition of our autocorrelation function there. So for starters, seems like the long way around, but if you compute the autocorrelation function, then at lag 0 you have the average power. Also, the autocorrelation function shape is well defined, and it's conjugate symmetric, and this comes directly from the definition of the autocorrelation function above. And not only that, but it has a peak at a lag of 0. Furthermore, it tends to decay over distance. And so as you go to infinity, the autocorrelation function just looks like the mean of x squared. So a typical autocorrelation function then might look something like this. At a lag of 0, we're going to have our peak. This would be the average power. Next to it, the values tend to taper off. Now you may have some functions that don't purely taper off, and if you have strong periodicity, you get periodicity here as well. But the autocorrelation function is even, or conjugate symmetric if it's complex, and it tends to taper off down to the mean. Now if the mean is 0, it's going to taper off down to 0. So we can also estimate our autocorrelation function from data, and we often do this, but to lead off, let's first throw this down. I realize we haven't actually written this yet anywhere. If we want to approximate the mean, and we have a Whiteson stationary process, we can just do that by averaging L values and dividing by L. In similar manner, if we want to estimate the autocorrelation for each mean, we find the product of two samples at that delay and average them together. Okay, so basics. But now the autocorrelation function comes in to help us in another situation. Suppose we are interested in the frequency content of a stationary random process. We know how to get frequency content. We use the DTFT that we've introduced earlier. So the first thing we might want to try is the DTFT sum of our random process x of n. But the problem is, because x of n never dies out, this won't converge. The sum will continue to grow as we add more values of n into it. And so, in summary, the DTFT does not work. Well, obviously I wouldn't have brought this up if we didn't have an alternative. And since it's in the discussion about autocorrelation, you're correct to assume it has something to do with the autocorrelation. So we're going to define capital Phi e to the j omega is equal to the sum over all m of phi xx, our autocorrelation function, e to the minus j omega m. And this will give us the power spectral density. It's something that we've defined. That's a very useful thing. In fact, we'll find later, as we look at this, that it behaves in much the same way as a squared spectrum would behave in nearly everything that we would be concerned with. A few useful properties of this, and then we'll spend some more time talking about it in our next lecture, is that it's real. Also, it's symmetric when x is real. So finally, we will see next that it has the same properties as if we had, say for example, taken the DTFT of some signal h, maybe our impulse response, and squared it. So that's why we call it the power spectral density. The spectrum would be a DTFT of something, and then we square that, and that would give us the power as a function of frequency, hence power spectral density.